here today, so I'll be covering quadratics by myself today. So thank you everyone for joining, and today we'll be learning about quadratic equations, what they are, basic factoring techniques, and how we can apply them to basic AMCA problems, as well as problems that you'll see in standardized tests such as the SAT and the ACT, as well as contests in at the high school level, such as the AMC 10 and the AMC 12. So without further ado, let's review some basic concepts that we covered the last session, and we'll be building on those techniques for more advanced concepts. So, oh man, is my my computer's lagging. All right, okay. My computer lagged for a little bit. Sorry about that. All right, so I'll just be going over a little bit of what we covered last week, and we'll be going over more advanced tricks that you'll need to tackle quadratic problems on the AMC 8. All right, let's get started by just reviewing what we covered last week. So last week we introduced the idea of distributing a term over a set of terms. So what I mean by that is that if you take this first example, 3 times x plus 5, you're distributing the 3 to the x and the 3 to the 5. So essentially what multiplying 3 by the whole expression x plus 5 gives you is 3 times x, which is just 3x, plus 3 times 5, which is 15. And so we also introduced the notion of factoring an expression, which is basically writing an expression in terms of a product of 2 or more expressions. So basically, if we claim that 3 times the whole quantity x plus 5 is true, then we can say equivalently that 3x plus 15 can be factored into the expression 3 times x plus 5. And so we can say that we're factoring 3x plus 15 to become 3 times x plus 5. And so we can also do this with more than one term in an expression, more than two terms in an expression. So in the first case, we have a binomial. We usually call this a binomial because bi is basically the prefix for 2, and nomial is just basically like a set of terms. So x plus 5 basically is a binomial because it has 2 terms. And so here we can actually use the distribution technique for more than 2 terms. So in this case here, we have 3 terms, x and y and z. So when we distribute 3 to this whole expression by multiplying 3 and x plus y plus z, you get 3x plus 3y plus 3z. And essentially, you're just multiplying 3 to every single one of the terms. And so that's basically the general idea of distributing a term to multiple terms. And so you can extend this idea to essentially any number of terms when you're distributing an expression to another one. So we can apply this notion of distributing a term to multiply expressions with more than one term in each parentheses, if you know what I mean. So in this example, we have the multiplication through x plus 5 and x plus 3. So you're multiplying x plus 5 and x plus 3 together, and with that, you're just basically doing the same thing, the same distribution process, except that you're doing it with each of the individual terms. So with x plus 5 times x plus 3, you first multiply x by x plus 3, then 5 by x plus 3. And so you can write it as x times x plus 3 and then add 5 times x plus 3. And then you can obviously use the normal distributive property on each of these two sub expressions. The idea of FOIL is basically extends this idea in a more concise manner. FOIL is an acronym for first out, inner, and last. So basically, this is a really useful technique for multiplying two binomials. So let me show you what I mean. So when you have the multiplication, x plus 5 times x plus 3, you can first multiply the first terms of each expression. So the first terms are x and x. And that will give us a product of x squared, obviously, because x times x, that will just become x to the second power. And I just wrote it as x times x here so that you'll see what I mean when I expand out the product. And the next term, the next set of the terms we want to multiply are the outer terms. So the outer terms are basically like the ones on the outsides of the multiplication. So those terms will be precisely x and 3. X and 3, because those terms are on the outer edge of the parentheses. So multiplying these outer terms will give us x times 3. And you can see this product right over here. So that's our outer. And then you can do this similar process for the inner. So the inner will be 5 and x. So the inner will be 5 times x. And then you can see it right here. You just add the product. And then the last will be just 5 and 3, because those are the last terms of each binomial. And so when you do this simplifying process, you will eventually get x squared plus 3x plus 5x plus 15. And you can combine like terms, which are the x terms in this case, to get x squared plus 8x plus 15. And so that's basically how you multiply binomials. It's basically the same thing as distributing a term to each term in another parenthesis. So essentially, you're just distributing the x to the x plus 3, distributing the 5 again to the x plus 3. That's all there is. And you can do this with any number of terms in each expression. So last week I gave a very vague example. I'm going to clear it up a little bit this week. So if I had something like x squared plus 2x plus 1 times x plus 3, you can still do the same process. You just need to multiply every pair of terms together and add those products. So you can distribute, let's say, x squared to the whole expression x plus 3. So you can just write x squared times x plus 3. And then you can distribute 2x to x plus 3. And then you can guess what comes next. Just a 1 and x plus 3. And then this is just normal distributive property, because you can just multiply x squared by x and x squared by 3x. And you can do the same process with the other ones. This doesn't really have much to do with the concept of quadratics, but it's very important to recognize that when you have like multiple expressions in a succession, like multiplied by each other, you just need to pick out one term from every parentheses. So let's say you get like x squared and 3. So exactly one term from each parentheses and add all of the products together. So you multiply like the terms that you just chose and add them up. But you just got to be careful that you can't have repeated products. Like you can't have x squared and 3 like twice. So that won't necessarily work out. Okay, cool. So now this brings up the question of factoring a quadratic. And so basically what does it mean to factor a quadratic? Well, let's actually first define what a quadratic is. So last week we covered that a quadratic is in the form of ax squared plus bx plus c, where a, b, c are unknown variables. So you can technically have constants for a, b, and c as long as you always have an x squared term. So typically you can just remember that a quadratic is an expression with 2 as the highest power. So you must have something squared in the expression. So now we know like what a quadratic is. How do we factor a quadratic? Well, let's revisit our factoring technique here, right here. If we factor 3x plus 15, we're going to get 3 times the whole quantity, x plus 5. And basically that's a way of saying that we can rewrite 3x plus 15 into a product of 2 expressions, 3 and x plus 15, x plus 5. Now with quadratics, we can write the quadratic in terms of a product of binomials. And so what I mean by that is that if you have let's take a more concrete example right here. If you have x squared plus 8x plus 15, you can rewrite the quadratic as x plus 5 times x plus 3. So essentially, you're undoing the distribution that you carried out earlier. So remember that like when we introduced distribution, we were multiplying pairwise terms here, right? So we use FOIL for first out, inner last, and then we combine the like terms to get this expression right here. Well, now with factoring, you're basically undoing the factoring right here. Sorry, the distribution. So we say that we factor the quadratic. We factor the quadratic x squared plus 8x plus 15 into x plus 5 times x plus 3. So if we were asked to factor like the quadratic x squared plus 8x plus 15, we would be expected to somehow, in some method, some way, write the quadratic as x plus 5 times x plus 3. And let's discover like a couple methods to do that. So again, math is all about connections, and it's really important to see whether or not we can find any connections back to previous problems or previous concepts that we've covered. And this is a really good example of doing that, because one of the really nice ways that we can factor a quadratic is by recognizing common patterns that appear within factorizations. So one factorization that we covered like 2 or 3 weeks ago was the difference of squares. So the difference of squares factorization tells us that when you have the quantities x plus y multiplied by x minus y, you get x squared minus y squared. And so you can prove that out. You can prove that using FOIL, right? If you actually like multiply like every pair of terms, you will eventually get x squared minus y squared. And so how does that help us factor a quadratic? Well, you can substitute, let's try substituting y equals 2. So when you have y equals 2, when you substitute y equals 2, you get x plus 2 times x minus 2 equals x squared minus 2 squared. And that's x squared minus 4. And so that's one way we can factor a quadratic. You can, if you have like a difference of squares. So again, this is a square, this is a square, because x squared, well, that's something squared, right? And 4 can be written as 2 squared. You can rewrite the difference of squares as a product of the sum and the difference. And so that's x plus 2 times x minus 2. Same thing with this factorization, x plus y squared, which will give us x squared plus 2xy plus y squared. And again, you can substitute values in for y. And same thing for I guess this is kind of like the same thing, but you're just switching the sign of the 2xy term. So with the square trinomial factorization, x plus y squared, you're gonna get x squared plus 2xy plus y squared as the expanded form, and similar process results from x minus y squared. We're just flipping the signs of the 2xy as seen here. So instead of x squared plus 2xy plus y squared, you're going to get minus 2xy in our expression. All right, cool. So I'm gonna write it like above here. So our special factorizations are a really good way of factoring special quadratics that fit one of the common factorizations that we've seen before. So special factorizations, and it's really important to make good notes of these, because factorizations, because these will pop up a lot, especially difference of squares in contest math. So x minus y times x plus y will give us x squared minus y squared. X plus y whole squared will give us x squared plus 2xy plus y squared. And then x minus y will be the same thing, except you're going to have a minus in front of the 2xy instead of a plus. All right, so these are the special factorizations, and they will come up time after time, so you should probably be very familiar with these. So if you are taking notes, you can just like, I'll give you like a few moments to get these down. All right, cool. So let us proceed with some other methods of factoring quadratics. So we introduced patterns, what I call patterns. Technically, they're just special factorizations that you should know. But sometimes like the quadratics are really nice, and you can just like think of a special factorization and just apply it, and then it becomes real easy. But many other times, the quadratic will not be like it will not be in the form of a special factorization. All right. So because this is a little bit messy, I'm going to clear this out a little bit. This is what Sid covered last week. You can check it out in last week's video on our YouTube, and also on last week's email. So I'm going to introduce today what's called the box method, because I made most of the mural depicted here. Sid didn't really know what I was talking about with like the box method, but basically it's kind of like my own name of like guessing and checking. some of the harder quadratics that you may see. And so that I'll be introducing to that to you today. So let us see. Let's see. So one of the really nice ways that we can factor quadratic is just by finding common factors. And so if you think back to this first expression right over here, the common factor of 3x and 15 is 3. Technically, you can factor it like in other ways, but for now, for simplicity's sake, we're gonna say that we can factor out a 3, which is our common factor of 3x and 15. And so that will give us the product of 3 and x plus 15, x plus 5. So let's see what we can do with common factors. All right, so our first technique that's not like special factorization is common factors. All right, so what can we do with this? Basically, the whole idea behind factoring like through common factors is finding the greatest common factor of like a sequence of terms. So if you have something like 3x squared plus like 18x, right? You can basically find the common factor of 3x squared and 18x. And so what I like to do when I find the common factor of these two terms is to look at the lowest well, first I look at the constants. So so I looked at the greatest common divisor of 3 and 18. And that's just going to be 3 because 3 divides 18 and 3 divides 3. So because like 3 divides itself. And once you divide out like 3 from 3 and 18, you're not going to find any more common divisors out of these two numbers. So the greatest common divisor of 3 and 18 is 3. And then I look at the lowest power. So what's the lowest power of x? Well, x is just x to the first, so this is just x. So this is for variables. And so we can say that the greatest common factor is just 3x. So this tells us that we can factor 3x out of the expression. So what results in the parentheses? What should we multiply 3x by in order to get 3x squared plus 18x? Well, we can, because we're multiplying 3x by something to achieve like the result on the left-hand side, we can divide by 3x. We can divide by 3x. We can divide the left-hand side by 3x to get whatever is in our expression. And so that will give us 3x squared over 3x, which is x, and 18x divided by 3x is 6. And the division I wrote there was just for visualization purposes. If you actually divided the whole thing by 3x, the 3x on the right hand side would cancel, but I don't want to do that because I just want to show you what the factoring looks like. And so we can write 3x squared plus 18x will give us 3x times x plus 6. So that's how we can factor quadratics using common factors. We basically find a common factor. We find the greatest common factor. So the greatest common factor. Common factor. Pen's a little goofy right now. All right. greatest common factor. That's basically kind of like the main intuition. It's very similar to factoring out the 3 from 3x plus 15. You just want to incorporate the variables too. All right. So now let's go on to another method called grouping. So grouping is when we group the terms. And I'll show you what I mean by that. It's kind of doing mini factorization. So I'll just write mini factor. And like I would, in my opinion, I think grouping would be a little bit hard to see, even though like most teachers at school like teach like grouping as one of their like first methods. I would say it's a little bit harder simply because like you would need to see how to break up the middle term, the middle x term in a quadratic into a sum of terms, and then like using grouping with that. But I think that would like need some intuition that I guess most students wouldn't see. So I'm gonna introduce the idea of grouping and it may seem a little bit arbitrary, but sometimes it can be very useful in factoring like cubics, expressions with x to the 3, so x cubed, or like polynomials of higher powers. So sometimes that tactic can be very useful. And so with grouping, let's take for example, our original quadratic, our first quadratic that we covered, right? So x squared plus 8x plus 15. So there's something really, really cool that we can do with this expression. So if we remember that 8 equals 3 plus 5, we can write this quadratic as x squared plus 3x plus 5x plus 15. And so that, what can we do with that? How can we write the quadratic in terms of two binomials? Does anyone have any ideas? If we split up the middle x term. Well, let's check this out. Consider the first two terms. The common factor between x squared and 3x is just x. So we can factor out an x out of the first two terms. And so factoring out the x will give us x times x, because x times x is x squared, plus 3, because x times 3 is just 3x. Then the common factor of 5x plus 15 is 5. So you can factor out a 5. And what results in the expression inside of the parentheses will be x, because 5 times x is 5x, plus 3, because 5 times 3 is 15. And so look what we just did here. If you let this be y, if you just let x plus 3 be like a variable y, you can write xy plus 5y be the expression that we just wrote in terms of x plus 3. So this is really nice because we got y's in our sum of products. So since y is a common factor, we can factor out y. And this will just be y times x plus 5. And since we made the substitution y equals x plus 3, we can just substitute back x plus 3 in for y. And that's our factored expression. So it's really nice here because the main step was writing 8x as a sum of smaller terms. So what those smaller terms does for us is that we can find a common factor, which is a binomial, and factor that out of the whole expression. So once you get more experience with factoring, you can just go from this step right over here to x plus 5 times x plus 3, which is really nice. Because if we looked back at the FOIL-ish expression, like I wouldn't like recommend FOIL just like just because like it would seem like mechanical when you're like multiplying expressions with like more terms. But basically in this example, remember how we can distribute x to x plus 3 and 5 to x plus 3, right? So you can see how that connects back to this example, right? So when we wrote 8x as the sum of 3x and 5x, we can basically find a common factor of x plus 3 in the first two terms and the last two terms, and you can basically factor that out. And it's basically reversing the distribution of the two binomials. That's essentially what factoring is all about. It's kind of, I like to think of factoring as the like reverse distributive property. You're trying to reverse everything, the tedious multiplication that you've done to get that polynomial, and then trying to get like a product of several terms together. And so our product here would be x plus 3 times x plus 5, which is the same thing as the quadratic above here. And so whenever you're factoring a quadratic, right, you want to make sure that every must have every expression in the product must have an x. So in this case, we have an x and an x plus 3 term, and the x and the x plus 5 term. Because if you have like one x and then no x's in the two expressions, right, you're not gonna form a product of x squared, because you must have at least two x's to form x squared, something x squared. So 5x squared, 3x squared, negative 3x squared, right? If you have like x and then no x, you're at most going to form a factor, or you're going to at most form a term of x. So you're not going to find something like x squared. So that's something very important to note here. Okay. So that's grouping by factoring. The main idea between like grouping and common factors is basically trying to trying to extract a common factor by rewriting the expression like cleverly. So with common factors, you can just immediately exploit the greatest common factor of the two terms, and you can just factor that out. But if you have like a constant term in like this expression, it's not going to necessarily work out. So if you have like 6, right? 3x doesn't really divide 6. So in those cases, you will want to try grouping, or try another one of the methods that we're going to cover. So that's grouping and common factors. Let's see what I mean by the box method, which is one of my favorite methods of factoring quadratics, which is basically, it's kind of like a technique of like guessing and checking. But actually, it's a huge credit to my mom, like for showing me this when I was like in like 5th or 6th grade, when I was trying to like learn how to factor these like complicated quadratics, and it works really well. So let's start off by seeing what we mean by guess and check, and then I'm going to show you the box, like the box method. We can also call it rectangle method. So if you have this, right? If you want to factor this, let's consider the general form of a factor quadratic. So rather than trying to factor this immediately, right, let's consider x plus a times x plus b. So let's FOIL that out. Okay, maybe not FOIL that out, but like let's distribute every term. So x times x is x squared. X times b is xb. A times x is ax, or just xa. And then a times b is ab. And then again, we can combine like terms. Which will give you x squared plus x times a plus b plus ab. Because we want to combine the coefficients of the x. Okay, so that's interesting, right? If you start off with a factored form of a quadratic, and let's say the coefficient of x squared is 1, because there are obviously going to be quadratics that don't have a first term of like the leading coefficient. We call the coefficient in front of the highest degree the leading coefficient. So here the leading coefficient is 1. We're gonna obviously see some quadratics which have like a 2x squared, a negative 3x squared, or something like that. But that for now, let's assume that the coefficient in front of x squared is 1. And so this is really nice because we know that if you have like a factor quadratic x plus a times x plus b, where a and b are, constants that we don't really know the value of yet, we know that the coefficient of the x term is the sum of a and b, and the product will just be the constant. So the constant will be a times b. So that's kind of nice, right? And if you look back to our example right here, and we can use that fact to really, really quickly figure out what the expanded form is. So let's do this without FOIL. Let's not FOIL or expand or distribute this out. So we know that there's going to be an x squared, right? Because in front of the x terms is just 1. If you have something like x and negative 3x, on the other hand, you're going to have something like negative 3x squared, which in this case, we're not going to find. So since the coefficients in front of the x are both 1, we're going to have an x squared. And now look at what we can do. For the x term, we can just add 3 and 5, and that's just going to be 8. And then the constant is just going to be the product of 3 and 5, which is 15. There you go. No need for distribution. Now, let's go back to this example and see how this can help us find like constants a and b to factor quadratics of this form. All right, so this is going to be a very fun game. Let's take the quadratic x squared plus 17x plus 70, right? Now, assuming that we can factor this example quadratic into a product of two binomials, x plus a and x plus b, we can say that we want two numbers, a and b, such that their sum is 17 and their product is 70. All right, so that's the game. So can you find two numbers, a and b, such that a plus b is 17, so the sum is 17, and the product ab is 70? So does anyone have any ideas? There you go. Yes, correct, Hubert. So you can find a equals 10 and b equals 7, as Hubert mentioned. You can switch up the values. You can say b equals 10 or a equals 10, a equals 7. It doesn't really matter here because we're factoring. Our goal is to factor this quadratic, and switching up the order, like, it doesn't really matter because you can let this be b and this be a. It doesn't really matter. It's just the same thing flipped around. So a equals 10, b equals 7, and once you have the pair, like once you have a and b, you're done. Because you can write the quadratic as x plus a, which we know is 10, times x plus 7, which is 7. And that's our factor form. The main part is just finding these two numbers with the sum of 17 and a product of 70. Because the rest is easy. Once you know a and b, well, you just kind of plug it into this general form. All right. So that's all cool. What do I mean by the box method? This is going to be really cool. Well, yes. Yes. So it's kind of like the same thing that you just did with the guessing, right? So the box method basically kind of controls basically you want to find the first two terms here. So like these are the first two terms, and you want to find the last two terms. So if you think about it, you can split up like each expression here in terms of the first and the second term. So this is the first term of x plus a. This is a is the second term of x plus a. X is the first term of x plus b. B is the second term of x plus b. And so if you think about it, right, we already factored this quadratic, x squared plus 17x plus 70. So let's write something, the result that you will get from the box method, kind of like the box method, because you can just draw a box, right? So if you write the factor form, x plus 7 and x plus 10, like that, x plus 7, there's an invisible. Whenever we don't have a sign, we're just going to assume it's positive. So x plus 7 and x plus 10, right? What's really nice is that x times x, so the product of the first column is x squared. The product of the last column is 70, and the product of the crosses, the sum of the products of the crosses will give us 17x, because x times 10 plus x times 7 will give us 17x. And that's our middle term. And so we can kind of see how we can guess and check using the box method, right? So we just need to find two individual terms that have a product of the first term, which is something x squared, and we can find the two numbers that have a product of the last term, which is as a number, and find those numbers and variables such that the sum of the products of the cross you see here will sum to the middle term. Yes, it's very cool. So let's do that. Let's do that, and I'll show you how to extend it with coefficients that are not like 1 in front. So let's try another example. All right, so let me give you the quadratic. Let's do some negatives and stuff with signs now. Let me give you the quadratic x squared plus x minus 20. See if you can find the terms that have a product of x squared. So you're gonna have variables on the left hand side and numbers on the right hand side, and then have the cross, the sum of the products of the cross, right? Be 1x. I mean. All right, hopefully you had a try at that. So if you look at that x squared term, naturally you want to put something like that, x and x, because x times x is x squared. And for now, it doesn't seem like it's going to be something complicated, like, I don't know, 3x times a third x, right? It doesn't really seem like that because the other coefficients are integers, 1 and negative 20. So let's just put x and x for now and see what happens. Now let's think about negative 20 for a second. We can factor negative 20 in a variety of ways. And we can factor 20. Let's just first factor 20, right? It can be in terms of like integers. So 20 can be written as 1 times 20, 2 times 10, 4 times 5. And we don't need to do something like 5 times 4 because it's just the same thing reversed. But basically, if you want to factor negative 20, you just got to attach a negative in front of something. So you can have negative 1 times negative 1 times 20, 1 times negative 20. That you get what I mean. You just need to find a pair. You need to find a pair, one of these pairs, and a negative, and attach a negative on one of them, and then see if the sum of these two numbers is 1. Because when you do the cross thing, these are just 1, right? So let's try like negative 2 and 10. Let's try negative 2 and 10. So the cross, what would be the cross, like I don't want to say the cross product, but the sum of the products in the cross. What would that be? Well, x times -2 would be -2x, and then you add 10 times x, which is just 10x, and that's 8x. That's no good because you want a 1x. So -2 and 10 doesn't work. So you can just keep trying the like pairs such that the numbers have a product of -20 and the cross, has a sum of 1. And so eventually, let's try like -5 and 4. So 4x minus 5x, and that's -x. Well, that's very close because we want a 1x, but we ended up with a -1. So we just want to flip the sign somehow. So let's try instead with a negative attached to the 4. Okay, so -4x plus 5x. There you go, because -4x plus 5x is 1x, and the cross has a product of 1, sum of products of 1. So with oopsies, with that, once your cross is valid, you can factor the quadratic. X plus 5 times x minus 4. It's a little bit of guess and checking if like if that's your like your first time doing it, but once you get to once you get the flow of it, it's really cool. And so you can use this to factor essentially like any quadratic, at least with like integer coefficients. So if you have 2x squared plus, let me see, 7x plus 3, yeah, you can basically think like, okay, what two terms multiply to 2x squared? Hello. Hello, hi, June. That's just 2, and then we can try like, 2x and 2x, 2x and x, 3 and 1. Let's just try that. 3 times 3x, right? 3 times x is 3x, 3x plus 2x, that's 5x. That's not 7x. Let's try another one. Let's try, let's just flip it, right? 2x times 3, which is 6x. You add x times 1, which is x. So 6x plus x, that's 7x. Oh, that's what we have right now. So these are our two factors. So it's really fast. The main intuition, again, is just finding these numbers such that the product of the first two numbers is the x squared term. The product of the last two numbers is the last term. All right, cool. So that's how to, this is factoring, this is kind of like the box method. Yeah. All right, so there's one more method that you should probably know before we end the session, which is completing the square. So what does that mean? Remember the factorization x plus y squared? This is the factorization for perfect square trinomials. So if you see stuff like x squared plus 2xy plus y squared, you can factor it as x plus y squared, just undoing it, right? So completing the square is kind of a mix of, well, you obviously want to see like a squared binomial like this, but sometimes you can use the factorization of difference of squares to factor a polynomial. So if you have something like x squared, actually a perfect example is our first quadratic that we factored here. So x squared plus 8x plus 15. There's a really cool there's a really cool trick that you can use to complete a square here. And that is by writing the expression like such: x squared plus 8x plus 16 minus 1. So you may be like, well, where does the minus 1 like come from, right? So watch what happens when you factor, when you see that this underlying expression is just the perfect square trinomial with y equals 4. So when you plug in y equals 4, right, you're going to get like x squared plus 2x times 4, which is 8x, plus 4 squared, which is 16. X squared plus 8x plus 16 can be written as x plus 4 squared minus, just x plus 4 squared. And you have a minus 1 outside of that perfect square trinomial. And so if you know that 1 is 1 squared, and so another factorization, this is difference of squares. So you can write it as x plus 4 minus 1 times x plus 4 plus 1. We're essentially letting like x, instead of x, we're having x plus 4. Instead of y, we're letting y be 1. And so simplifying, we can get x plus 3 times x plus 5. And that, again, that's our factorization that we ended up with in our previous examples. All right, cool. I didn't really have time to go over the quadratics, like the quadratic formula. But yeah, so that's a really cool way of, factoring a quadratic. And so today, just to recap a little bit, we went over like what a binomial is, what a quadratic is, just some basic definitions. We covered the distributive property, how to multiply expressions with more than one term, like in each of the, like each of the expressions in the product, right? And we also covered like what FOIL is, the acronym, and how we can expand binomials. And building off of those ideas, we introduced the idea of factoring a quadratic, which is basically undoing the distribution. And so x squared plus 8x plus 15 can be written as x plus 5 times x plus 3. And so we saw a couple of different ways to factor a quadratic. So we use difference of squares, or rather the general term is kind of like special factorizations. So difference of squares and the perfect square trinomials. Basically the bottom two here. We also discovered that we can factor quadratics using common factors, grouping, and the box method, which is my favorite. With more practice, you'll see how quickly you can guess and check. And yeah. All right. So we also covered completing the square. All right. So next week we'll be covering new topics in number theory. So thank you very much for attending. And we'll be sending out a recap email with a video and the problem set. So thanks so much for attending. See you all later.